So Kalvik is a PhD student in the computer science department, and he works with Professor Sunivas Akila. He works in controls, mostly robotics, and today he is going to talk about probabilistic gas leak rate estimation using submodular function maximizations. So with that, Kalvik, we're really looking forward to hearing this exciting talk. So take it away.
All right, thank you so much for the introduction, Dr. Mehti. And with that, good morning, everybody. I am Kalvik Chakala, and the paper I'm presenting today is probabilistic gas leak rate estimation using submodular function maximization with routing constraints. I co-authored this paper with my advisor, Dr. Srinivas Akella, and it will be published in RAL next month. And I will also be presenting it at ICRA in May. I'll start by explaining the problem that we are addressing and the assumptions that we made, after which I will detail some of the prior approaches to the problem. That should give you a good background information necessary to understand our method, which is split into two parts: leak rate estimation and informative path planning. I will end the presentation after discussing some of the limitations of our approach, and will conclude soon after. Our paper addresses the fugitive gas leak rate estimation problem. What does that mean? It is often the case that oil wells leak harmful gases, such as methane, into the environment. But it is not possible to operate these facilities without leaking any gases. Therefore, we must monitor and notify the facilities of any major leaks that could be happening in the oil field. Now, this is a non-trivial problem. Environmental factors such as wind and temperature affect the dispersion of gases. It is also possible to have multiple simultaneous leaks in an oil field. Additionally, the sensors used to monitor gases are usually mounted on vehicles, which are of course restricted to road networks. We also have to consider the informative path planning problem to ensure that we only collect the most informative data while accommodating our distance budget, which usually depends on the amount of time and fuel your vehicle can handle. Now, given the problem's difficulty, we made a few assumptions to develop our approach. We assumed that the terrain in the oil field was flat without any substantial obstacles. We also assumed that the gas plumes from different leak sources do not overlap onto each other, and that all environmental factors such as wind and temperature are relatively constant during data collection. Additionally, we assume that the locations of all the candidate leaks are already known, which is usually the case since we know the locations of the oil wells. And I say candidate leaks because it is possible that of the known leak locations we have, only a subset of them are actually leaking. And if a particular oil well is not leaking, we just assume that we predict it as having a zero leak rate. So I have explained the problem that we are solving and our assumptions. I will now detail the prior approaches to the problem. The fugitive gas leak rate estimation problem has been addressed before. It was addressed by Pandey et al. With the method where they used satellite data to estimate the gas leaks. Project Astra is another interesting approach where they deployed a fixed sensor network in an oil field. Travis et al. Considered a neural network-based approach to predict these leak rates. Finally, Albertson et al. Developed the Bayesian approach to leak rate estimation. The Bayesian approach entailed fixing a prior distribution over the leak rates of each source. Then they used mutual information metrics to quantify the informativeness of possible data collection paths. The data from the field that was collected by traversing the selected path, which had the highest amount of information, was then used to calculate the posterior or the leak rates. The process was repeated until the leak rates converged to the underlying true leak rates. Our solution is based on the approach presented by Albertson et al. So let's dig a little more deeper into the prior work, what they did. That will give you a better picture of how we improve on it. Albertson et al. Modeled the prior over the leak rates with a GEV type 2 distribution, which is a heavy tail distribution. And the likelihood P of M given S, where M is a single data sample collected from the data field, which tells us the concentration of a gas in a particular location. Given the leak rate S, they modeled it using, the likelihood P of M given S models the probability of a collected data sample M given a particular leak rate S with an exponential function. Here, the function C is a gas dispersion model that can calculate the gas concentration at any given location when provided with the leak rate and the leak's location. The exponential function models the likelihood by measuring the similarity between a collected data sample and the simulated gas concentration at the same location where the data sample was collected.
Can I ask a quick question?
Of course, yes.
What is X, Y, Z? Are these the three-dimensional coordinates?
Yes, the X, Y, and Z are the locations, the coordinates of the location where the data was collected in an oil field. And these coordinates are relative to the oil well location or the leak source location that is being considered. Does that answer your question?
Right. If I may ask a follow-up questions, you assumed a flat terrain, so I was implicitly thinking it would be X and Y. Why there is a height Z? Did I miss something?
Oh no, that's actually a really insightful question, and the reason is we are modeling gas plumes, and the way these plumes behave depends on environmental factors such as humidity and altitude. If your entire oil field is at a high altitude, your environmental pressures and so on are going to change how this plume is going to behave. So we still have to consider the Z coordinate to be mindful of how these factors affect our dispersion.
Okay. The Z will be same for all the.
Yes, that is true.
Okay, thank you.
But although it's not something we consider in our experiments, it is also possible to use aerial drones to collect data, at which point Z will play an even bigger role because your data points come from arbitrary heights as well. So the problem with Albertson et al.'s approach is that the prior distribution they had considered makes the posterior distribution, which is the probability of a leak rate S given the collected data samples M, make it intractable to analytical computation. Since a posterior cannot be computed analytically, the authors use computationally expensive numerical quadrature-based integration techniques to evaluate the posterior, which increases the computation time by a substantially large amount. Now that we have all the background information about the problem, I will move on to detail our approach. We addressed the high computational cost of the posterior by using a Gaussian distribution as the prior over the leak rates. If the likelihood is also a Gaussian distribution, our posterior would be a Gaussian that can be analytically computed. But our likelihood function has this nested gas dispersion model, which appears somewhat convoluted and unlikely to result in a Gaussian distribution. However, we were able to factorize this gas dispersion model as the product of the leak rate S and a function of the location where the gas concentration is computed. Since this factorization is linear in the leak rate S and the likelihood is an exponential function, our likelihood is also a Gaussian distribution. Once we made the prior a Gaussian distribution and ensured that the likelihood is also a Gaussian distribution, we derive the posterior, which again is going to be a Gaussian distribution. The capital M over here is a set of data collection samples that were collected from the oil field. And the bold capital A is a vector containing the outputs of the factorized gas dispersion model with unit leak rate. Because Gaussians can be computed analytically, its computation cost is linear in the number of gas concentration data samples. We simulated a gas leak and a single gas leak and calculated the gas concentration at 10 different locations to validate our approach. We used the simulated data samples to predict the true leak rate using the original GEV type 2 prior-based approach and our Gaussian prior-based approach. We see that our approach converges to the true leak rate. And furthermore, in a real-world scenario, gas concentration samples have much higher sampling rates. Over here, we only use 10 data samples. And because these sensors have higher data sampling rates, it would give us a lot more data to base our estimates on. Therefore, we believe that our approach would be on par with the GEV type 2 based approach in a real-world oil field. Also, note that the computation time difference here is 5 orders of magnitude faster. It's 5 orders of magnitude apart, which is substantial. What this means is the prior approach would have required an entire workstation and substantial amount of time to compute these results. But our approach, you could deploy it on something as small as a Raspberry Pi. Okay. I briefly mentioned this before. The leak rates distribution is also used to compute an information metric over possible paths. The path with the highest amount of information is selected for data collection. We validated if our Gaussian prior-based approach would assign well-calibrated information values to different paths. We did this by computing a single leak source, by considering a single leak source and calculating the information value for a road parallel to the leak at varying distances along the x-axis. Our results show that our approach sorts the 6 considered paths by their information value in the correct order and can do so in a fraction of the time compared to the prior approach. Before I move on, does anyone have any questions they would like for me to address?
Sorry,
oh, yes, please go ahead.
I am not familiar exactly with how GP and Bayesians. I'm very new in the field, but what is the assumptions behind using the GP? Is it like the uniform distribution?
So when you see GP, I think you meant the
Like a
Gaussian
Gaussian
prior.
process. Yeah, Gaussian process.
We are not using Gaussian processes. We are considering Gaussian distributions. It's a one-dimensional Gaussian distribution.
Oh, okay.
A Gaussian process assumes you have multiple Gaussian distributed random variables and that they can be modeled as a multivariate Gaussian. Over here, we consider individual oil wells, which have a leak rate, which is scalar. A leak rate could be 0 grams per second or 10 grams per second. So it's a single random variable, which is Gaussian distributed. So yeah, does that answer your question?
Yes, yes.
All right.
Thanks.
Sure thing. All right. So thank you for the question. And our experiments and discussion so far assumed that we already have data samples from the oil field. I will now go over our solution for the informative path planning problem, which decides where to collect the data samples such that we get the maximal amount of information from the oil field. So informative path planning is again not a new problem. It has been addressed before by numerous authors. Our variant of IPP, though, is intrinsically different from the conventional problem. When solving the IPP problem, one is usually concerned with getting the maximal amount of information about an entire data field. However, we are only interested in getting the information relevant to estimating the leak rates of the oil wells, instead of estimating the gas concentration in the whole oil field. Therefore, most IPP approaches do not apply to our problem. Albertson et al. Addressed this problem by using a brute force algorithm. They iterated over every possible path within their distance budget and selected the path with the maximal amount of information. They use expected entropy reduction as the metric, as a mutual information metric, which measures the informativeness of the paths. But the approach is far too naive and does not scale to large graphs, since there could be an exponential number of possible paths within the distance budget. Additionally, it is possible to have many of these paths that don't even approach any of the leak sources and be completely uninformative. We address the IPP problem by leveraging the inherent structure of our information metric, which again is the expected entropy reduction, EER. It is known to be a submodular function. Now, submodular functions are set functions that have a diminishing returns property. This means that adding more elements to the solution set diminishes the size of the increments of the function values. So if you consider this picture here, visualizing submodular functions, you have two sets, a set A and a superset B. What submodular functions say is, if you have a variable or another term you would like to add to either of these sets, the output of the function value would be much smaller when you add this term to the larger set B compared to the smaller set A. So why does knowing that EER is submodular help us solve the IPP problem? Well, the generalized cost-benefit algorithm is designed to maximize submodular functions while imposing node routing constraints. We can use the algorithm to construct informative paths by selecting data collection regions that maximize the EER. It also ensures that we get a valid path by imposing node routing constraints. The algorithm even has a runtime approximation guarantee, and it is computationally faster than the brute force algorithm. But here's the catch. The GCB algorithm only considers node routing constraints. We need to impose arc routing constraints to use the algorithm in a road network. All right, so what is arc routing now? And how does that differ from node routing? The node routing problem requires one to visit either all or a subset of nodes in a given graph. The TSP is a node routing problem. But in arc routing, we need to visit either all or a subset of the edges in the graph. And depending on the graph's connectivity, we might have to add additional edges to our solution to ensure that it is a continuous path. An example of arc routing is the snow plowing problem, where one has to traverse every road to clear snow while minimizing the total travel distance. Garbage collection, mail delivery, and network maintenance are similar problems that can be solved using arc routing. Our problem has to be solved as an arc routing problem because our data collection happens along the edges of the road and not at the intersections, which are modeled as nodes in the graph. Once we realized that our objective function is submodular, the GCB algorithm can be maximized using submodular. I'm sorry, let me get that again. Once we realize that our objective function is submodular, the GCB algorithm can be used to maximize submodular functions with routing constraints, and that there is such a thing as arc routing, we merge them together. We replaced the TSP solver in GCB with an arc routing problem solver. The GCB algorithm was inherently modular enough for us to be able to make this change. Furthermore, it still allowed us to retain the approximation guarantee of the algorithm. The arc routing problem, or ARP variant of the GCB algorithm, can be used to solve our IPP problem in road networks. Additionally, we found that if the routing solver was a deterministic function, the GCB algorithm converged to the solution path well before the end of the algorithm. We leveraged this inherent property of the algorithm by adding a simple break statement which could check for convergence. And once the condition is met, the solution would be returned immediately. This allowed us to improve the computational efficiency of the GCB algorithm. And yeah, by the way, the GCB algorithm itself, the vanilla version was developed by someone else. We just improve. We generalized the algorithm to arc routing and improved the computational efficiency of the algorithm. I mentioned this because I forgot to add the reference for the algorithm. My bad. At a high level, the GCB algorithm selects one edge in the graph at a time and adds it to the solution path. It computes the increments to the path cost upon adding each available edge to the solution from the previous iteration. It also calculates the increments to the EER of the paths after adding each edge. The edge with the highest EER to route cost ratio is added to the solution set. The algorithm is repeated for the remaining edges until either the distance budget is met or there are no more edges to add to the solution. I'm going to present my results. Do we have any questions before I get into that?
So Kalvik, there was a lot of material on the slide.
Mm-hmm.
So perhaps ask for questions, and maybe if using your pointer, you can walk us through the highlighted blocks of the pseudocode one more time.
I think we
Sure.
are from here. So this arc-routing process limits you to just meet each edge once in the whole process.
Not necessarily. So the way we construct our solution path is, let me go back to another slide over here. Yeah. Is given our graph, what the GCP algorithm is doing is it's selecting edges to traverse, which it believes have high amounts of information. And we do this by selecting one edge at a time. So the algorithm computes the route cost to the, or rather, let me begin from the beginning. At the beginning of the algorithm, we wouldn't have any required edges to traverse. But after the first iteration, we would have a single edge to traverse. And we would compute the route cost as using the arc routing problem, such that we start from the depot and we come back to the depot. And we also make sure that the required edge has been traversed. Now, once we finish the first iteration, in the second iteration, we select another edge, which we believe is going to be informative, given the fact that we have already acquired the data from the first edge. And to do that, to make the decision, we compute this EER to route cost ratio. The route cost would be the cost of the route such that we visit both the required edges now. And the EER would be all the information we get in traversing whatever path you get upon solving your routing problem. And we repeat this process. We keep adding more and more edges until our distance budget has been saturated, or the entire graph has already been traversed. Of course, more often than not, your distance budget is going to run out well before you cover the whole graph. And that's what the algorithm is doing. The inner for loop over here, it measures those ratios of EER to route cost. The first line is computing the increment in the EER. And the second line is measuring the increment in the route cost upon adding a particular edge. Once you get those ratios on line 13, we use the ratios to select the node which has the highest ratio. And of course, we have our break statement here, which breaks out of the algorithm instead of traversing over all the permutations of the graph once the distance budget has been met. So yes, does that answer your question?
Yeah, thank you.
I got a question.
Yes.
What is exactly the argmax referencing? Is it basically the max of the deltas or the maxes of the?
The ratio.
It was just argmax. So it's the max ratio of the deltas.
Okay. Let me rephrase that. It says argmax because it's saying the edge which has the ratio, the EER to route cost ratio, which has the highest EER to route cost ratio. So we don't want to just select that ratio. We want the edge which has the maximal ratio. Hence we use an argmax instead of just a max.
Okay.
All right.
So Kalvik, regarding the previous question, would it be correct to say that ideally we would like routes that don't traverse an edge more than once, but it may be the case a edge gets traversed more than once?
Yes, spot on. That is correct.
Can I ask a couple of
Of course.
questions?
Yes, please.
You may not have to answer it all now. We can discuss at the end of your talk, but the way the algorithm is written, it seems like a greedy algorithm that picks the highest cost and it keeps going on. I do understand that submodular function has this greedy property that you are at least 70% close to the optimal solution or something like that. I know that you proved that EER is a submodular function, but I do not necessarily see that this C hat function, that's the arc cost, being submodular. And I also do not see whether the ratio that you consider in line 13 to be a submodular function. So at any point, if you want to comment on that and suboptimality of your approach, that would be nice.
I like that question. That's very, what's the word? It's a brilliant question. It took me a lot of time to understand that very question and be able to wrap my head around the algorithm. And you are right. Yes, the routing algorithm is not a submodular function, and this is indeed a greedy algorithm. And that's where that's the reason the approximation factor for this algorithm is a runtime approximation factor. What that means is, given the particular problem you're considering, the graph you're considering, the approximation factor changes. It's not going to say that the approximation factor is the same no matter which problem you pick. And the way the algorithm draws this approximation factor is by treating the route cost, the routing algorithm, as a submodular function. But because we know it is not a submodular function, you have a you bound it as a number, as in how submodular is the routing function when you're looking at this particular problem. So to a certain extent, it's approximating the routing function as a submodular function. And in doing so, you're able to come up with the runtime approximation factor. So yes, the approximation factor, I did not mention the actual number because it's going to vary depending on the problem. In some cases, you might be lucky and actually get that 60, 70-ish% of ideal submodular functions, which would be fantastic. But it is also possible that the bound is much looser than what you're hoping for.
Thank you. That makes sense.
Do we have any other questions? All right, I'll move on. Okay, so I explained our algorithm. Let me explain how it behaves. Let me go over the results. So we tested the performance of the GCB algorithm on a data set that we generated using real world data. We used the locations of the oil wells in the Permian Basin oil fields in Texas, USA. And we clustered the oil wells using k-means, and we extracted the road networks underlying each cluster. This gave us 134 graphs, each with a road network and the locations of the oil wells. We considered arbitrary leak rates for these oil wells that we have in each of our graphs. And as anticipated, we found that the GCB algorithm was noticeably faster than the path iteration algorithm, which is the brute force algorithm used by Albertson et al. But here's the thing, the path iteration algorithm rarely finished running within the allocated 20 minutes time budget for each of the considered graphs. The vanilla GCB algorithm also took the whole 20 minutes to run on each graph, but its solution quality was far better than the path iteration algorithm. Furthermore, our variant of the GCB algorithm, which we call MGCB, converged to the same solution as the vanilla GCB algorithm, but at a fraction of the time. We also tested our arc routing variant of the GCB algorithm against a TSP variant of the GCB algorithm. And as expected, treating the problem correctly using an arc routing solver gave us the best performance. And here's an example graph from our dataset. we see that the solution generated by the path iteration algorithm spends most of the time traversing the northwestern part of the graph where there are many oil wells, but it ignores the other regions.
Alvik,
Yes.
sorry to interrupt. Perhaps you could just explain the figure, what the dots mean and what the edges mean and so on.
Sure thing. So the blue dots are the intersections on the road network. The black lines are the roads themselves in the network, and the orange dots are the oil wells, and the colored paths shown in purple, green, and red are the solution paths generated by the corresponding algorithms. Also note that when we say modified GCP with RPP, RPP stands for Rural Postman Problem. It was named after a Chinese scientist, hence postman and not person. The reason it's RPP and not ARP is because RPP is a particular realization of arc routing problems, similar to how TSP is a single realization of vehicle routing problems, or VRP. So yeah, back to the figure. The path iteration solution spends most of the time on the northwestern part of the graph. The TSP-based solution, the TSP-based GCB solver-based solution also spends time on the northwestern path, but we see that it wastes some of the distance budget traversing this edge over here, where there aren't any graphs, any oil wells close to these regions. Now, when we look at the RPP or the ARP version of the GCP algorithm that we proposed, we see that it doesn't go too deep into that region where there aren't any oil wells. And it also goes further to the northeastern part of the graph. And it also traverses this edge over here in the southern part of the graph, which as a result gives us the lowest mean squared error, the lower the better, compared to the true leak rate that we predicted using our algorithm.
Sorry, what is the mean square error of what? I didn't catch it.
Yes, yeah, yeah. I just realized it wasn't clear enough. So what we are doing is once we collect the data from the paths that we have shown here, we use that data to predict the leak rate of the oil wells that we simulated for each of these graphs. And the mean squared error is measuring the error between the true leak rate and our predicted leak rate using our estimation method that we presented before. And of course, since it's an error metric, the lower it is, the better.
Okay, and then the orange dots are representing the oil tanks, right?
Yes.
But we are not saying that which one of them are leaking, do we? Like here, are you showing which one is leaking?
Yes, we chose not to show the leaks because it made the figure rather complex. But in reality, what happens is almost every tank is always leaking. And what we're actually more interested in is which oil wells are leaking at dangerous rates, which are harmful for the environment. So yes, depending on the simulated scenario, they all leak at different rates. However, when we benchmark the various algorithms for a particular graph, we simulated the same leak scenarios.
Okay, and the reason that your purple lines are going to like a top part of it is just because there are more tanks there, not because of the leaking, right? My question is, if the leaking is more concentrated on one side, all of them are gonna be kind of like a moving.
So that is
Because right now I don't know, like if the leaking is like uniformly distributed or.
I see. So what happens is we don't necessarily try to visit every tank. What we're interested in is considering the tanks which are more likely to leak. So if you remember from the first part of the talk, I mentioned we have a prior and a posterior distributions. The prior distribution we consider, we treat each individual oil well as a separate random variable, and each variable has a different prior. So if we have historical data for an oil well, which tells, oh, this particular oil well leaks very frequently, the prior would be much higher, would have a much higher leak rate. So the bias over here is primarily from the prior. But here's the good part. Here's the good part. Let's say you collected the data today. Now tomorrow, you believe that this similar tanks are going to still be leaking because not all of them have been fixed yet. So your prior has changed now. Before you only considered historical records, but now you have data from yesterday. So now your results are even more biased to what the real scenario might be happening there. Does that answer your question?
Yes, yes, thanks.
Okay.
So Kalvik, can I take another crack at Amir's
Sure thing, please go
question?
ahead.
So the paths that are being generated, are they offline paths, or are you updating the posterior after taking some number of measurements and then updating the paths?
So it's a bit of an offline online business going on here. This whole approach is recursive. We fix a prior, we plan a path, we collect data, we get the posterior, and then we repeat this process. The posterior becomes the new prior, and we repeat the process again. So the first iteration, when we have a prior, the path planning happens in an offline manner. We plan the whole path, and then we collect the data, and then we update the posterior in an offline manner. Once you have the posteriors, we essentially checked in with the environment, and we got a snapshot of the environment. And now we are using the information we have collected to repeat this process and plan future paths.
So are you doing this posterior update after, let's say, every edge that you traverse, or after traversing the entire path?
After traversing the entire path. So yeah, and strictly speaking, it is completely offline.
Okay, thanks.
All right.
So I had a question about, basically you were saying that if in reality, everything's gonna be leaking. So what would happen if, let's say the wind was going north? The one that's had is a dangerous leak, because that's what we're measuring for, is what you said. What if one of the top ones on the graph is the one that's dangerously leaking, but it's going north, so you don't get the measurement? You have.
I like that question. Yes, wind is a huge factor. And like you said, if the wind is blowing north, everything goes up north. And in this particular scenario, if the road network just can't reach there towards the northern region, you won't be able to realize those leaks. However, if you consider the oil wells in the southern part of the graph, if the wind is blowing north, in their case, a big portion of it overlays the road network. And in that case, you will be able to collect the data for those particular nodes. Now, do we account for wind? Do we actually model these things and factor that information? Yes, we do. If you remember our likelihood that we considered, which had a gas dispersion model, I mentioned at the beginning of the talk, it actually accounts for the wind direction. So at the beginning of the problem, before we go for data collection and planning, we in practice, what happens is we check the weather, we see which way the wind is blowing. And with that in mind, we assume that the wind has been blowing in the same direction over the whole data collection period. And in doing so, we account for the direction of the wind and make sure that we avoid going into regions where, because of the wind, you wouldn't see any gas. Does that answer your question?
I'd be
Okay.
interested in the results from that.
I'm sorry?
Seeing some of the results from that or data regarding that, just with other wind.
So all our experiments that when we benchmarked, we considered different scenarios from outlined by the EPA, where they tested particular scenarios and collected real world data in terms of temperature and everything. And we used those measurement readings. So I don't have individual scenario examples to show you, but the benchmark is diverse enough to account for varying wind conditions.
So I think, Kavik, the question is for the same leak rates, etc. If you had different wind directions, would you see different paths? I think that's the gist of the question.
Yes, that is correct. And yeah, I suppose that's what I was trying to say with my answer. Depending on the wind condition, the path is going to change. Of course, one thing to note is we assume that during the whole path planning and data collection phase, the wind direction stays in that particular direction. If it keeps changing during the whole period, that's when things get very dicey and our approach wouldn't hold very well. Which is actually a good segue into our next section. By the way, I'm going to move on. Do we have any other questions or?
I have a quick question, sir.
Yes.
Well, in this one of these figures, could you please show me where your robot or vehicle is starting and how it is traversing the path?
I see. I do not remember the depot location off the top of my head. So afraid I don't have an answer for it.
Okay, fair enough. My next question was going to be, there are some edges which are like dead ends. So you will go there and then you have to backtrack, right?
Yes.
So my question is, in that case, that particular edge is traversed twice because it's a dead end. Do
Yes.
you account for twice of the cost in your algorithm, or do you only account once?
It depends on what you, well, the cost is computed twice, the cost being the travel distance, but the information gain, which is the EER, that we only count once. Because once you're traversed, going back again won't give you new information.
Okay, so then C hat, whatever you had in your algorithm would be
Yes.
approximately changed depending on if you traverse twice or once. Okay.
Yes, exactly.
Okay, thank you.
Actually,
Sure.
that
Yeah,
as well.
please, go ahead.
What if it's a long path and during that time, you've already measured it once, is your algorithm going to update it if suddenly it becomes a dangerous leak in that time? Like what if something happened, it goes down the path, something happened while at one of the places you already measured, and then when you come back across, you register that or?
Yes, I like that question again. Yeah, these are beautiful questions and these are the limitations of my work. We are assuming a static environmental condition. We are assuming the leaks are fixed during our planning and data collection phase. But in real world, the environment is a lot more dynamic. So the question is, how do we address this? And unfortunately, right now, we do not address that. We assume everything is fixed. Because of that, we say once we traversed it, no matter how long the path, on the way back, the amount of information is fixed. Does that answer your question? All right. All right. So yeah, those are some beautiful questions, and everyone pretty much, I suppose, predicted my limitations for the most part. It was great to hear that. But let me just summarize the limitations of my work. Gas plumes. I said that we assume that these gas plumes never overlap. But in real world, these oil wells could be close to each other and they could cause overlapping gas plumes. In which case, what happens is our algorithm, there's a good chance that it assigns this gas to both the oil wells. And in doing so, it assumes that both the oil wells are leaking at much higher leak rates than what they really are doing. So this is something I'm going to address in my future work. And then there's source localization. Yes, in an oil field, oil wells are the biggest, most likely the biggest contributors of leaks. However, there are also oil tanks and pipelines which stretch miles across oil fields. And it's difficult to model them as a location that's known in advance for a potential leak. Because in that, if you discretize these pipelines, you would have a very large search space and it would complicate your inference procedure. So how do we address source localization problem if we don't know where some of the leaks are coming from? And then there is this last question we had, which was dynamic environmental conditions. Things are going to change. Wind is going to change. The leak rates are going to change. Temperature is going to change. How do we address this? And these are things I'm hoping to answer in my future work. And let me conclude with what I've done to sum up. We've addressed the computational efficiency limitations associated with leak rate estimation. We did this by considering a Gaussian prior distribution over the leak rates and factorizing the gas dispersion model. This, in turn, allowed us to derive a Gaussian posterior over the leak rates that can be computed analytically. We demonstrated that this approach converges to true leak rates and can be used for IPP, and moreover is 5 orders of magnitude faster than the prior approach. Our Bayesian leak rate model also allowed us to quickly compute the EER, the information metric, used to measure the informativeness of our paths. And we then used the GCB algorithm to solve our IPP problem. But because the GCB algorithm did not consider edge routing constraints required to apply the algorithm to road networks, we developed a variant of the algorithm that used arc routing. We also improved the computational efficiency of the GCB algorithm itself. We demonstrated experiments showing that our variant of the algorithm was at least 1 order of magnitude faster than other approaches. And here's what I would like for you to take away from this presentation. I hope that you consider the Gaussian assumption. Are you solving a problem where your particular phenomena of interest can be modeled using Gaussians? Gaussians are omnipresent in nature. Dispersion of gases can be modeled as Gaussians. There are models for forest fire smoke dispersion that can also be modeled using Gaussians. Water pollutants have been shown to disperse similar to a Gaussian. Then there is submodularity. Submodularity also appears in numerous objective functions. Set cover, mutual information, and influence of social networks, influence in social networks are submodular functions. Are you using a submodular function as your objective? And if you are, you can use greedy algorithms and still be able to come up with approximation guarantees for your solution. Also, as I mentioned, our variant of IPP is different from the conventional IPP problem. So are you looking at a problem where this kind of IPP might be a better fit than the conventional approach? Finally, how would you address the limitations of my work? How would you address the overlapping gas plumes, the source localization, and of course, the most interesting of all, dynamic environmental conditions? One last thing, my acknowledgements. The project was funded by NSF. My paper, you can access it on IEEE Explorer. All of the code I've used is available on GitHub and publicly viewable. I also made the derivation for my posterior and EER available there. And finally, I'd like to thank Saurav Agarwal, who shared his beautiful library line coverage for solving arc routing problems, public on GitHub. and also Dr. Eben Tama from the EPA, who helped us understand what methane is and how things work, and Syan Datta, who indulged me in some very interesting conversations about our problem, and my sister, Yitka Jakala, who made the super cool render of an oil field for my paper right here. Thank you.
Thank you. Nice presentation. Let's give it a big round of applause. We do have some time for questions, so if anybody has questions, comments. I can get started with one quick question. So you mentioned that your problem is not a traveling salesman problem because you have to traverse the edges, not the nodes. So isn't there a method called a dual graph that changes the nodes into edges and edges into nodes? And if you do TSP on the dual graph, would that work in your case?
Yes, that is correct. That is spot on. That's how the RPP solver we use works under the hood. I'm not sure about all ARP variants, but the particular variant that we look at, RPP, their algorithm, their proofs which show that any problem that is RPP can be converted to an equivalent TSP problem and then solved using a TSP solver. But it remains that you have to do this conversion step. Only then would the problem be properly addressed and you would get the correct solution.
Okay, thank you.
All right, then. Thank you everyone for listening and the wonderful questions. And I hope everyone has a pleasant weekend.
Thank you. Thank you.
Mhm.
It was great.
Thank you so much.